De Broglie was a young student in Paris, and he said, okay, light has been found to have this funny behavior. We thought it was waves, but it turns out sometimes it's also particles. Now, there are lots of things around which we've always thought of as being particles, things like electrons and so on. Maybe they sometimes behave like waves. Maybe what's sauce for the goose is sauce for the gander.
We think we understand particles. We think we know what things like billiard balls are. And when you say no, you have to think of these things as being wavy as well as being particle-like. You have to apply quantum rules to electrons. That was a really big step.
De Broglie came up with the remarkable idea that everything is a little bit wavy while he was still a student. The theory gave his tutors something of a headache.
De Broglie's examiners at the university were reluctant to give him a degree for such a fool idea. He got the degree all right, but only because Albert Einstein happened to be visiting Paris at the time and said, look, this isn't such a bad idea. Maybe it's even true.
Although Einstein championed the idea of wavy electrons, there was no experimental proof. In fact, quite the opposite. J.J. Thomson had got the Nobel Prize for proving it was a particle. But eventually, confirmation of the wavy nature of electrons did come.
The key experiments in the 1920s that proved that electrons are waves did so by firing electrons at the regular structure of a crystal, rather like the latticework structure we've got here. And those experiments showed the electrons bending round the atoms in the crystal, just as the waves here are bending round the structure of the pier.
George Thomson in the 1920s was involved in experiments that showed electrons behaving as waves, doing just the things that ripples on a pond do, being diffracted, interfering with one another, all those kinds of things. And the story culminates because J.J. Thomson, the father, got the Nobel Prize for proving that electrons are particles, and George Thomson, the son, got the Nobel Prize for proving that electrons are waves. And they're both right. That's really the core of quantum physics summed up in that. Both of those Nobel Prizes were deserved.
It was the best of times and the worst of times for the physicists. They were in the middle of a revolution. They were struggling to come to terms with a problem that still troubles scientists now. Is the electron a particle or a wave? Or both?
If you asked, so to speak, if you asked light a wave-like question, lo and behold, it gave you a wave-like answer. But if you asked it a particle-like question, it gave you a particle-like answer. It conformed to what you asked it to do. In that sense, there wasn't a direct contradiction. There was obviously a very deep puzzle about how such behavior was possible, but at least there wasn't a flat-on collision. It wasn't at the same time behaving like a bullet and like a spread-out flappy thing.
It's kind of like putting on two different sets of glasses and seeing the world in two different ways and being able to flip-flop back and forth between those two pictures. The general public doesn't have that ability, so they really see it as a very weird Alice in Wonderland world, and it disturbs them. Frankly, although I may seem very calm, it still disturbs me a bit too.
The disturbing nature of the electron confounded scientists in the 1920s. The Austrian Erwin Schrödinger set himself the task of writing down an equation that would predict how the wavy electron would behave. In 1926, he succeeded.
And in fact, it's a very simple equation. I could write it down on the back of an envelope with a great deal to spare. And here, in fact, it is. It simply has two terms in it. On one side of the equation is how things change with time. And on the other side of the equation, it says that's related to the energy of the system, which is the fundamental way of describing things in quantum mechanics. So there it is, a very simple equation. And the whole of atomic and subatomic physics, in some sense, flows from that equation. That shows you something of the wonderful power of mathematics to condense and crystallize out physical truth.
Although the behavior of the wavy electron could now be calculated, what no one could predict was that the wavy nature of matter was about to cause a major split between the quantum pioneers. If electrons were particles, it would be possible to know exactly where they were and how they would move around. Isaac Newton's laws of motion, written down in the 17th century, described precisely how particles of any size, from an apple to the moon, behaved. The certainty of Newton's world made the Industrial Revolution possible. The motion of anything could be predicted. The most intricate machines could be built. They ran as reliably as clockwork, just as Newton imagined the whole universe to work. It seemed unquestionable that nature was utterly predictable.
Newton's equations tell you exactly what's going to happen in the future. It turned out that the quantum world, the small-scale world, is different from that. It's unpicturable to us, it's cloudy in its character, and it's probabilistic, meaning that we can't say for certain what's going to happen. This may happen, that may happen. We can say what the chances are, but that's as far as we can go.
The man who first realized the world runs on quantum chance was Werner Heisenberg. In 1927, he proposed the uncertainty principle. It states that because matter is spread out in space, wavy, it's impossible to say exactly where it is and what it might do next simultaneously.
This is absolutely real down in the depths of quantum physics. An electron itself does not know where it is and where it's going.
So we can never be certain about what's happening inside an atom. The effects are so small in our everyday world, we never see them. But the fact that at its heart, nature is a game of chance, meant scientists had to concede there was a real limit to what they could know with certainty. For many, this was unacceptable.
Several of the quantum pioneers didn't like what they'd invented. Max Planck wasn't really happy with it. Einstein wasn't happy with it. Schrödinger wasn't happy with it. And Einstein hated the idea that the outcomes of experiments could not be completely predictable. And in the famous expression, it's usually quoted, he said that I cannot believe that God plays dice with the universe.
And he thought that meant that the physical world had to be absolutely objective, had to be absolutely determinate and clear and certain. And of course quantum mechanics wasn't like that, and so he came to hate his grandchild.
From across Europe, the greatest minds of the age came together to settle the matter of uncertainty. The place was Solvay in Belgium. The year was 1927. The single photograph that remains of the conference shows a unique collection of scientific genius. Max Planck is next to Marie Curie. Behind Einstein are the other great doubters of uncertainty, like Prince Louis de Broglie, the original proposer of the wave theory. And on the top row, Erwin Schrödinger, whose equation made mathematical sense of wavy matter. Schrödinger and the others were not willing to take the leap into uncertainty with the young Turks Pauli and Heisenberg.
They've said, we've got to go with the new physics, that's the way the world is, you can't quarrel with that. And there's some quite sharp arguments and discussions between Einstein and Bohr on the one hand, and between people like de Broglie and a very sharp-tongued Swiss physicist Wolfgang Pauli, who essentially told de Broglie, I think, to shut up. He was being stupid. And de Broglie was a sensitive person and didn't like that, and he actually went away and did shut up. So it was a sort of turning point moment in which the young Turks won out over the old guard.
He couldn't believe that the outcome of an experiment depended on chance. And that's what led Einstein, for the last 20 years or more of his life, to fight this more or less lone battle against the theory that was taking physics by storm and try to find flaws in it. And he kept trying to invent experiments, thought experiments, imaginary experiments that would prove that quantum physics couldn't be true. And every time he did, people found ways round his thought experiments and found that they didn't prove that at all. And ultimately, perhaps just as well for him, after he'd died, people actually did some of these experiments for real, and every time they found quantum physics is right, probability rules.
By the late 1930s, quantum theory had found a new home, as European scientists sought sanctuary from Nazi oppression.
So there was this huge shift of science to America. You have this rich country and you have this ability to apply massive technology and money to fundamental problems.
But Americans, by and large, have taken quantum mechanics as a very useful tool and said, oh, don't bother me with all these philosophical arguments. I just want to be able to make calculations. And that's where our strength is, that we have taken this pragmatic viewpoint and ignored what are some troubling aspects. If we really sat down and thought about the philosophical meaning of what we were working with, we might not get anything done.
The company that had already made a fortune from knowing the electron was a particle were by now exploring the commercial potential of the wave theory of electrons.